Okay. In lesson 7.6, and it'll happen in lesson 7.7, we've been talking about exponents all chapter. Yeah. So now it's kind of applications of exponents. And so today we're looking at exponential functions. So we're going to talk about what is an exponential function, and we'll look at a graph of an exponential function, things like that. Okay? So, an exponential function is a function of the form y equals a times b to the x. Okay, so anytime it's of the form a times b to the x, it's an exponential function. The key really, notice, where is the x? Where is the variable?
It's on b.
Yeah, it's on b. It's in the exponent. So right there, because the x is in the exponent, that's what tells me this is an exponential function. Okay, when the x is in the exponent. Now notice it does say a cannot be 0, because if a is 0, this whole equation is 0. And b greater than 0 just says b has to be positive. And it can't equal 1. Because, you know, if those things are happening, you're going to have just 0 or 1. It's not going to really work. But basically, a can be anything other than 0 times some number raised to a power. That's what we're looking at. Okay, so kind of what I've already talked about, ways to identify exponential functions. First of all, it's of the form y equals a times b to the x, and important there, x is the exponent. Another way to identify if something is an exponential function form, if it's an equation, that makes it easy. X in the exponent. A table, if we're looking at a table or like an XY list of numbers, a table where all X values have a constant difference and Y values have a constant ratio. So if X values have a constant difference, that means they have a constant amount added between them. Okay, so if they have the X values have a constant difference, they have a constant amount added between them. And the Y values have a constant ratio, means they have a constant amount being not subtracted, multiplied. Okay, so, and I guess when we say add, subtract, maybe I didn't think about it, but you should say add / subtract. Okay, so constant difference, same number being added or subtracted. On the x's, y's have a constant ratio. So, part of what we're doing today in the notes is, does this represent an exponential function? So, y equals 3 times 6 to the x. I don't know.
Because the exponent is an x.
Okay. If you look at the form, y equals a times b to the x, here's the key. X is in the exponent. If x is in the exponent, then, yes. And I'm going to say it is in the form y equals a times b to the x. However, I also like, Michaela, you said x is in the exponent, right? That's also a valid, true answer as well. Okay, I'm not against that either. Maybe I'll even put x in exponent. Can you guys see the orange okay?
Yeah.
I just realized I was using orange and sometimes it doesn't show up as well. Okay. Okay. Next example here. Y equals 2x. Is this an exponential function? Does it match the form y equals a times b to the x? Why not, Jacob? Okay, exactly. The answer is no, and the reason is Yeah, there is no exponent. I was going to say x is not in the exponent as I'm saying, but yep, all the same. Technically, if I want to get picky, there is an exponent. There's an exponent of 1, but definitely x is not in the exponent. Okay. Let's look at these tables. And again, we're trying to identify, do these represent exponential functions? Oh, goodness, excuse me. Now, what was the shortcut I gave up above? Go back and read it then. Okay. X values have a constant difference. Y values have a constant ratio. What do I mean X values have a constant difference? They add or subtract. So, look at your X's. How do you get from 0 to 1?
You add 1.
How do you get from 1 to 2? 2 to 3. So does it work? Okay. Now, what do the Y values have to do? But how? They have to be constant multiplying. So like last time it was plus 1, plus 1, plus 1. It has to be multiplied by the same number. So, how do you get from 2 to 6? In terms of multiplication? Times 3. How do you get from 6 to 10?
Times, I don't know, that's so weird. Like 1 point something.
So what's important there? She says times some weird 1 point something. Okay, valid answer.
It's not the same.
So here's the deal. Is it multiplying by 3? No, it is not multiplying by 3. That's the key. It's not multiplying. Here's the deal. If you can identify the first one's multiplying by 3, all you have to be able to identify, does the next one multiply by 3? And it does not. So what do I know now? Right. This is, no, it is not exponential. It is not an exponential function. And my reasoning, the Y values do not have a constant ratio.
Okay, this makes sense now.
The explanation makes sense now.
Yeah, I have no idea what you're talking about.
Yeah, that's why I always give examples. The rule up above may or may not make sense until you see the example. So you have to give the example a chance before you totally say, I don't get it. So. Okay. Can we check B then, or the next example?
Mm-hmm.
So what am I checking on the X's?
It's adding the same number.
Jacob says plus 1, plus 1, plus 1. Is that okay? Is that a good thing then? Yeah, because we're adding or subtracting the same number. What are we checking on the Y's? Times 2. Does it work again?
Yes.
Okay. Frowny faces at top and I don't know what down at bottom, but okay, times 2 times 2 times 2. Did it work?
Yeah.
So, is this represent an exponential function?
Yes.
Yes. And if you're looking for a reason, yes. X values had a constant difference. Y values have a constant ratio. X values have a constant difference.
I would have been here probably sooner if Miss Sexton and Mr. Reed talked to me, because they thought, because I go by Jacob, they thought forgot all about, Miss Sexton did. Then I go by Jacob and she was like, why is he there?
Man, what are you talking about?
When I got my iPad, I would have been here a lot sooner.
What does that have to doing? Let me think.
To keep me focused from not falling asleep. I'm tired. I mean,
Okay, so I wrote that yes, this is an exponential function. X values have a constant difference. Y values have a constant ratio. Okay? So these notes will be helpful if you have to answer similar questions in homework, of course. Okay, next set.
Okay.
Evaluate each function for the given value. Any clue what we mean by evaluate? Kind of, yeah. When we evaluate, we want to know a solution. What does it equal? In this case, it says f of x equals 6 times 2 to the x for x equals 3. So if it says for x equals 3, what am I going to do?
6 times 2 to the third.
Yeah, every place I see an x, I'm going to replace it with 3.
Oh, yeah.
So officially, it's f of 3 we're trying to find, but it's 6 times 2 to the third. Jacob, do you remember what we have to do first mathematically here? Yeah, the exponent. So 2 to the third means 2 times 2 times 2.
8.
And then we have 6 times 8.
40.
I was just going to say, can we do that without Lily? She seems to be the queen of multiplication in here. Depends on what the numbers is. That's right. I remember the conversation. She was the queen of nines the other day, right? Yep. Oh, 6 times 8 is 48?
No, it doesn't. But it sounds the same.
Yeah, I was saying that's not a rhyme. I don't know what to call it, though. But yeah, I know what you mean. Okay, so evaluate. Don't freak out about it. It just says for x equals 3, so 3 goes in for x. What am I doing over here with g of x? Okay. We're plugging in negative 2. So the math we're going to be doing is 45 times 3 to the negative 2.
Oh, yeah.
Or negative second. Okay, before you can do any actual math, like multiplying or anything, what do we do with negative exponents? Move it to the denominator. So now 45 is going to stay 45. 3 to the negative second is going to become 1 over 3 to the second. And if you want, what is 45 as a fraction? 45 over 1, yes? So then, what did you say? Okay, you can cross out the ones. What about 3 squared? 3 times 3, which is 9. So then officially I have 45 over 1 times 1 over 9. Then what do I do with 45 over 1 and 1 over 9?
Well, 45 times 1. I don't know.
Well, keep going with that. I like that. 45 times 1 is 45. 1 times 9 is 9. One more step. 45 over 9. Mm-hmm. 45 divided by 9 is?
Something. I can't count that high. I need a calculator.
9 times what is 45? No?
Oh, 5.
5, yeah.
Uh-huh.
I had to
Excuse me.
It's a Friday. I'm tired.
I am too, as you can tell. So I just gave a big old yawn.
Oh, so it's
Yeah.
5.
And I guess technically, if you want, we could say 5 over 1, but 5 over 1 is then just 5. I'm not doing any crazy math right now, I promise.
Yeah.
We'll save crazy math for another day. Okay. What about a population example? One of the common examples of exponential equations is growth and decay. And population, well, we hope it's, an example of growth. So, I see words. What's the first thing I should do with this problem?
Underline everything is actually
Okay.
That's what I was going to say. Underline the keywords.
Okay. And I always just teach the first step as being read the problem, yes? But if you guys are underlining important words, you're going to be reading the problem, aren't you? So yeah, I always just start with just reading it. An initial example of 20 rabbits triples every half year. The function f of x equals 20 times 3 to the x gives the population after x half-year periods. How many rabbits will there be in 3 years? Thoughts?
okay. Well, x is 3. Right now.
Nope, I agree.
Yes.
It's asking how many rabbits will there be after 3 years? Well,
Okay, so 3
Well-
is,
hold on. We have to be a little careful with that. It does say 3 years.
yeah, but it triples every 6 months, so it would
Good.
be 6 times.
Yeah. One of the important pieces of information to write down is what is x? Or to underline, I guess, is what I meant. But x is half-year periods, right? So x is half a year. 2 x's is then a whole year, right? So if we're talking 3 years, how many half-year periods is that? 6, right? Because every 2 halves. So 3 years is going to be 6 half-year periods. And the key to notice there is, what is x then? X is 6. So always read, what do they want x to be? They're trying to be tricky here, but we're not going to let them win. Okay? What am I going to do with that x? Yeah. Did they give me an equation?
Yes.
I love when they give me an equation. It makes life so much nicer, doesn't it? So, we're putting in 6. F of 6 is 20 times 3 to the 6th. What are we doing first? Exponent. 3 to the 6th. You gonna do the mental math for me, Jacob?
You do want the math.
You gonna do the mental math for 3 to the 6th? He's gonna start. And we didn't go that high on the paper the other day, I don't think. Yeah. Okay. Calculator says 729.
I'm not good at that.
Yeah, 3 to 6, this gets a little big. Okay, and
It's times 20.
729 times 20?
140. 14,580.
14,580 what?
Rabbits.
Yeah, the question asked how many rabbits. So that's a lot of rabbits. And that's just after 3 years. I know. Most math students hate word problems. However, the idea that I love the idea that you guys say, okay, underline the important information. Exactly. That's why I say start by, okay, read the problem. Look for the important information. In this one, it was wonderful because they gave me an equation, right? They told me x is half-year periods. That was the tricky part. Now,
Is it got a graph too?
we do have to practice graphs.
I hate graphs more than
I hate math Excel's graphs. 'Cause they're so.
They are a pain, aren't they?
I don't like typing answers in Excel. It's so hard to
Would you guys want to save the graphs for Monday?
Please.
Because otherwise, I'm afraid we're going to go right up to 3 o'clock.
Yeah.
So now, here's the deal. If I stop here, though, can you hop on Math Excel and do a little work?
Do I have to do the whole thing?
No. No.
Oh, well, just if there's graph problems, just don't do that.
Just skip those, right?
Okay.
And I honestly don't remember what there is in the way. There are some that involve graphs, but they don't all involve graphs. So
Will do.
what I'm going to say is hop on Math Excel, work a little bit. Jacob, I guess you could work on either assignment. And then Monday we'll finish graphs there.
I just remember I found